Oral presentations by the research scholars. We have Mintu Porel from IIT Palakkad and Deepak Chopra from IISER Bhopal as the evaluators of oral presentations. And we have a total of 6 presentations. Each presenter gets 8 minutes for presentation and 2 minutes for question answer session. So precisely, so please stick on time. You have the time tracker here. Please have a look into that and do accordingly. I first invite Lakshmi V. Menon. Please come. Kumar Jha, please come to the front row of the stage.
V. Menon from Kochi University. My topic is crystal structures, band gap analysis, and anti-cancer study of a novel quinoline-based dihydrazone and its self-assembled double-stranded helical nickel complexes. These are the outline of my presentation. Since we have chosen a quinoline derivative as the carbonyl compound, let me give a brief introduction of the quinoline derivatives. Quinoline is a heterocyclic aromatic compound with a nitrogen atom in the ring with various properties such as multi-density, tunable reactivity, and rigid structure. Among various applications of quinoline derivatives, we have chosen the coordination chemical applications of the quinoline. We have chosen the nickel-2 as the complexes of quinoline derivative, which have shown many applications in catalysis, petrochemical industry, medicinal chemistry, etc. From various biological applications, we have selected the anti-cancer activity because of the selective cytotoxicity, tunable coordination, synergistic effect of the nickel helical complexes. Moving on to the experimental method, here we have synthesized the ligand 110-base quinoline 2-carbaldehyde adipic acid dihydrazone by reflexing quinoline 2-carbaldehyde and adipic acid dihydrazone for 2 hours. The structure of the ligand was primarily established by the elemental analysis. Subsequently, the ligand was reflexed with the nickel perchlorate salts in methanol chloroform solvent mixtures to form the complex 1, which is NiL2. Here also the elemental analysis was carried out to establish the structure of the complex. For biological studies, we have chosen the A549, which is the lung cancer cell lines for the anti-cancer assessment using MTT assay, and DMSA as the control. The percentage of viability was calculated by the given equation. Moving on to the results and discussions, the ligand and the complex was characterized using absorption and IR spectroscopy. And the band gap was calculated by dot plot and UV-DRS spectra. The structure of the ligand was established using single crystal X-ray analysis, which shows that the ligand crystallizes in triclinic crystal system with P-1 space group. The table shows the selected bond lengths and bond lengths of the ligand. And here the figure A shows the various intermolecular and intramolecular hydrogen bonding interactions, while the B shows the unit cell packing diagram of the ligand along the B-axis. Then we have performed Hirschfeld surface analysis to find the intermolecular interactions. Further, we have established the structure of the complexes using a single crystal X-ray analysis. Here also the complex crystallizes in triclinic crystal system with P-1 space group. Here, figure A shows different intermolecular and intramolecular hydrogen bonding interactions with the packing diagram of complex 1 along C-axis, and the figure C shows the coordinating atoms of the nickel atom. For theoretical studies, we have chosen B3LYP631GDP basis set for the ligand, and the band gap from the theoretical studies was calculated as 4.02 electron volt. And for the theoretical studies of the complex 1, we have chosen 6311GDP for non-metal atoms and LAND L2D set for nickel 2 atom. Here, from the theoretical studies, the band gap was calculated as 2.54 electron volt. The in vitro anti-cancer assessment study shows that at low concentration, both the ligand and complex does not show any particular activity. However, as the concentration increases, both the ligand and shows some anti-cancer activity as shown from figure A and figure B. Summary, we have synthesized a homotopic helical nickel-2 complex of a novel hexadentate dihydrazone ligand, and the structure of the ligand and complex 1 was established using SCXRD studies. Hirschfeld surface analysis of the ligand was explored and found out that the SH contacts are the highest contribution to the Hirschfeld surface. The solution state, solid phase and the gaseous phase band gap of both the ligand and complex 1 was determined. And the anti-cancer study of the compounds was screened against A549 lung cancer cells shows that at 100 microgram per ml, 21.19% and 30.33% of the lung cancer cell lines was destroyed by both ligand and complex. Acknowledgements. Thank you.
What has the band gap to do with the biological activity?
Biological activity can be related by band gap. As the band gap decreases, there is a high chance of good biological applications.
Why is that?
That I don't know.
Also, nickel is added, right? Nickel, any metal, is a problem, right? So, can you tell me how nickel will be eliminated if you were to take this particular drug?
Nickel complex itself shows some biological activity.
No, my question is how nickel will be eliminated from a biological system after its function.
Nickel is an essential element, so it's itself in our body. So as all other process, I think it will be eliminated by the usual biological process.
Hi, nice presentation, Lakshmi. So I have one question that I think you synthesized an imine bond, right?
Sorry, ma'am?
You have synthesized an imine bond, right?
Yes.
So we know that in the acidic condition, stability, it is not very stable, right?
Yes.
So and cancer is a acidic condition. So what is your comment that in the cancerous cell, is it stable, your compound?
We have synthesized the ligand in an acidic condition, so it will be stable.
Okay. So that pH is stable.
Yes.
Okay. And did you test the cytotoxicity?
Sorry, ma'am?
Cytotoxicity?
No.
Okay. So it will be your maybe future experiment, right? Okay. Thank you.
Thank you, Lakshmi Menon. Next presenter is Aman Kumar Shah. Please come out to the stage.
Myself, Aman Kumar Jha. Good evening, one and all. Myself, Aman Kumar Jha from Central University of Tamil Nadu. And today I'm going to present my work here. My work is to synthesize the spirooctahydroquinoline using the transition metal palladium catalyst and organocatalyst. So let's have an overview for my work. It's divided into 4 parts: introduction, optimization, library, and applications. So just have a look on introduction. I'm going to discuss very few about organocatalysis, organocatalytic Diels-Alder reaction, transition metal catalyzed cycloisomerization, and some natural product related to lepidine alkalides and the synthetic approach. Why organocatalyst? Organocatalyst, it's clear from the name that it's from organic molecule. It's having non-toxic and environment friendly, and having mild reaction condition, and it gives better enantiomer selectivity and diastereoselectivity selectivity for better synthesis of natural products, and that having biological activity. So here is the first organocatalyzed Diels-Alder reaction done by David Macmillan in 2000 with his co-workers, and for his this work he got Nobel Prize in 2021 along with Benjamin List. In this one, he used amine-based chiral catalyst for the enantioselective cycloaddition, and he got 84% of yield and 89% of enantioselectivity. Next, have a look on transition metal catalyzed cycloisomerization. That is our key reaction. So, in recently 2017, Anderson did the palladium state and BBA-DA ligand based for cycloisomerization reaction with a better yield, and we use this reaction as a key reaction in our work. Have a look on this natural products, all having the octahydroquinoline and decahydroquinoline as a base structure, and from this one we got the idea to synthesize our lepidine alkaloid based the natural product, the mimic of the natural products. It's a marine natural product having anti-cancerous and anti-malarial properties. So just see how to synthesize this. This is just a 4+2 cycloaddition product. We need one diene and dienophile. And the previous step of this diene is eneinamide. To synthesize this eneinamide and dienophile, we are having the multi-step synthesis. Dienophile is synthesized from its corresponding isatine, and E9-amide is synthesized from its corresponding alcohols. This is a synthetic approach for the reaction. First we did palladium-based cycloisomerization, then 4+2 cycloaddition. We'll discuss this more about this in optimization. In optimization, we screened many catalyst, organic catalyst and solvent. In that one, we found that DCM and C3 catalyst, that is quinine catalyst, is the best catalyst and solvent at the room temperature. So after that, we increased the temperature to 50 degrees Celsius, and we found that DCM at 50 degrees Celsius giving the better yield and the phenomenal diastereoselectivity. So this is here the best optimized condition for our reactions. After optimizing the reaction, we went through the library of the molecule by changing the dienophils. If you see, you will find the mild to excellent yield in this reaction, but perhaps here you see the bromine and iodine substituted having the less yield, comparatively less yield because of the esteric factor. And when we change the protection on nitrogen, we also found that there is a less yield because here Bock is going to supply the electron to this dienophile, make it more reactive. And in this one, that electron-rich species is not there to make it more reactive. That's why here yield is decreased. The same thing happened with allyl and proposyl protection, and we got the comparatively less yield. And when we changed the group on the ester, I mean tertiary butyl we took, due to the steric factor here also we got the moderate yield. After that, we changed the N protection completely to the methyl, and in this one also we got the excellent to moderate yield, only this tertiary butyl having the less yield due to the steric factor. So all compounds are characterized with the NMR, HRMS. Just have a look on the typical NMR. Here, that oxygen attached CS2 resonates at 3.8. I mark some important peaks for understanding the molecule structure. Then this proton resonates at 2.9, and the next, this 2-methyl, resonate at 2.5. And here we are having 2 tertiary butyl group. One is oxygen attached that resonate at 1.6, and another one that resonate at 0.9. And after that, we are having 2-methyl that is attached to the silyl group. That's why we got that peak at the around 0, that peak resonate at 0. And here we are having the diastereotropic protons. So we got the quartet of AB doublet here. Just have a look on the C13 NMR. Here this carbonyl peak appears resonate at around 170 to 180, and this amide carbonyl resonates at 150, and these two tertiary butyl resonate at around 30, and these 2 methyls resonate at 22. And this silyl methyl resonate at -5. To understand the stereochemistry of the compound, this is the crystal structure of compound. From this crystal structure, we came to know that the configuration of this molecule. After that, to better understanding the reaction condition, we did some control experiment. In that one, we found that we can't go without the quinine catalyst. Quinine catalyst is needed for the hydrogen bond only catalyst is needed for the reaction to be done. Next, from the crystal structure, through the crystal structure and control experiment, we came to this plausible transition state. Here, quinine is going to approach the dienophile, So I sum up the conclusion that we successfully demonstrated the Diels-Alder reaction for the stereoselective synthesis of novel spirooctahydroquinoline. All molecules were well characterized with NMR, HR, MS, and IR. Stereochemistry is confirmed through single crystal XRD and submitted to microbiology department for the biological activities. I want to thank my supervisor for his support throughout my research work. Thanks to Central University Chemistry Department for lab facilities, SIR for their project funding, UGC for my, uh, and last but not least, Farooq College for giving me this stage and opportunity to present my work in front of you.
The presentation is now open for discussion.
I have no particular discussion point, but key point is to keep the time. You look at there, you also look at this. This is very important for a student. Okay?
Yes.
The second point that I would, well, timing is very important. At the same time, you also have to get to one thing quickly and not to present too many things. So this lost your time. These are only ways of training students. We are not evaluating your scientific credibility for a job. We're looking at your capacity to present. Thank you.
DCM 50 degrees Celsius, right?
Ma'am?
DCM, right?
Yeah.
You did the reaction in DCM
Yes, ma'am.
and in 50 degrees Celsius.
Yes, ma'am.
So we know that boiling point of DCM is very
40
low.
degrees Celsius.
So how did you handle that reaction?
Ma'am, we took a close vial to perform the reaction. In that one, we heated it up to 50 degrees Celsius. But that vial was totally closed in such a way that there is no leakage, and whatever solvent vapor came, that was inside the reaction, reaction vial only.
So did you reflux? Did you reflux?
No, ma'am, that
Oh.
closed vial only.
Okay. Thank you.
Thank you, Aman Kumar. Next presenter is Amrita TP. Please come on to the stage.
Afternoon all. Today I would like to discuss topic on nitrogen doped carbon dot as fluorometric sensor for ferric ion sensing in water. We are all aware of the importance of iron in our daily life. Its deficiency causes anemic condition in body and it is taking part in the cellular metabolic activities. Its high concentration in water causes turbidity and clogging of pipes. Hence, its detection is highly significant. Different ferric ion detection methods are atomic absorption spectroscopy, ICP, MS, spectrophotometry, and fluorometric sensors. Among these, fluorometric sensors are high selectivity, high sensitivity, and faster detection method. Different fluorometric sensors are metal organic framework, metal nanoparticles, carbon dots, semiconductor quantum dots, and dye-doped materials. Nowadays, carbon dot are taking attention because of its low toxicity, good biocompatibility, high water solubility, and excellent photostability. Carbon dots are luminescent nanoparticle with size less than 10 nanometer with graphitic core and functionalized surface. Like any other nanoparticles, its different synthesis methods are bottom-up and top-down method. Different top-down method involves arc discharge method, chemical oxidation, and electrochemical processes. Different bottom-up processes are hydrothermal method of synthesis and microwave synthesis and thermal decomposition method. Here we are using hydrothermal method for the synthesis of carbon dots. Move on to the present work. It involves the synthesis of carbon dot from citric acid as carbon source and orthophenyl diamine as nitrogen dopant under hydrothermal condition for 160 degrees Celsius for 8 hours, and we obtain a blue luminescent carbon dot. It is well characterized using TEM, XRD, XPS, FTIR, and UV spectroscopy, and the synthesized carbon dot is used for the ferric ion sensing. And move on to the characterization. XRD analysis shows that it contains 3 peaks at 23.4 degree, 42.6 and 60.8. And the peak at 23.4 correspond to 002 plane with interlayer spacing 0.37 nanometer, which is similar to the interlayer spacing for graphitic carbon. And TEM analysis shows that
it has a lattice fringes with a d-spacing value 0.21 nanometer, which is corresponding to 100 plane, as we can see from the XRD analysis. Move on to the XPS analysis. It shows the doping of our nitrogen to the system, and the deconvoluted spectra shows that it contains lots of surface functional groups. And the surface functional groups is also confirmed from FTIR spectroscopy. Thus, we have synthesized carbon dot with size 2.4 nanometer with carbon core, graphitic with pyrrolic and pyridinic nitrogen. And the surface contain hydroxyl, aminoxy and epoxy groups. Move on to the optical characterization. UV visible spectroscopy shows that it contains 5 peaks, one at 236 nanometer corresponding to pi to pi star transition of C double bond C, and the peak at 268 and 273 nanometer correspond to pi to pi star transition of C double bond O, and the peak at 293 correspond to pi to pi star transition of C double bond N, and the peak at 373 correspond to N to pi star transition of C double bond and other lone pair containing groups. The PL spectrum shows that excitation and emission spectrum of carbon dot with excitation at 350 nanometer and emission obtained at 436 nanometer. And further study shows that our carbon dot shows wavelength independent emission. And the luminescent decay study shows that lifetime of synthesized carbon dot is 4.57 nanometer, and the synthesized carbon dot show excellent photostability. And move on to the application. We have used the synthesized carbon dot for the sensing of turn off as fluorometric sensor. And extent of quenching with addition of anylates shows that only ferric ion shows maximum quenching for the carbon dot luminescence. With the addition of ferric ion to the carbon dot, its luminescence is gradually quenched. And with relative quenching efficiency shows linear relationship with concentration of ferric ion with a limit of detection 35.7 micromolar. We have now checked whether our synthesized carbon dot is interference-free sensor. So we have analyzed relative quenching, and it shows that with ferric ion it shows maximum relative quenching, and we have now checked whether our carbon dot is quenched by other anylates. Without carbon dot, its quenching efficiency is too low, and with the ferric ion with other anylates, its quenching efficiency is improved. Thus, our carbon dot can be used as interference-free sensor. Move on to the mechanism. We have used absorbance spectroscopy, PL spectroscopy, and luminescence decay study for identifying the mechanism. Absorbance spectra shows that even after the addition of ferric ion, there is no additional peak is observed. So, possibility of static quenching can be excluded. Now, we have checked the decay studies, which shows that the decay lifetime is not much altered in the case of even after the addition of ferric ion. The possibility of FRET, PET, and dynamic quenching can be excluded. Let's move on to the next analysis. We can see that absorbance of ferric ion overlap very much with the excitation spectra of carbon dot. Thus, in our case, the quenching mechanism is due to inner filter effect. Now we have analyzed the efficiency of synthesized carbon dot in real water samples, and we obtained a result with error less than 5%. Move on to the conclusion. Now we have synthesized carbon dot and nitrogen doped carbon dot using hydrothermal method, and it is well characterized using TEM, XRD, XPS, FTIR, and PL spectroscopy. And the synthesized carbon dot is used as a fluorescent sensor for ferric ion with a limit of detection 35 micromolar, and inner filter effect is proven to be the mechanism of quenching in our system. And carbon dot is effectively used for real water sample analysis. Thank you.
Nice to see these results. I wanted to ask you, what is nitrogen doing in comparison to regular quantum dots?
What?
In comparison to regular quantum dots, which have no nitrogen, what is nitrogen doping doing? Is it better?
but compared to our citric acid system, its luminescence is highly improved and its wavelength also shifted to red.
Why is it? Why is that this is better, an iron 3 plus sensor? Is nitrogen involved in the binding with the iron?
Nitrogen doping only improves the luminescence properties of the carbon dot.
It is not involved in binding.
Yes.
How do you know?
Here in mechanism, only the quenching is only occurred by the absorbance of energy that we are given to carbon dot. It is absorbed by our ion system. So,
If you were to say that nitrogen is not involved, what will you do? If you were to say that nitrogen is not involved in binding, what will you do to prove that?
Hi, nice work, Amrita. So, did you taste Fe2 plus? Because I saw in your metal selectivity, Fe2 plus, did you?
no, we have checked only Fe3 plus.
Maybe you can check Fe2 plus. That would be good, huh? And also one thing is that when you have 3 ways, what motivated you to choose the hydrothermal method?
Hydrothermal most easily method. Compared to other method, it is a more easy method, so we choose an
Easy, like it has any advantages or anything?
Hydrothermal method. Easily we can compare to other method, it is more easy to conduct in our lab. So we choose.
Okay, thank you.
Next presenter is Maimuna Paloli. Naslina P also come to the front row.
Paloli. Today I am here to present our recent research article on adsorbed carbon monoxide enabled self-terminated AU grafting on PT6 NGs for enhanced methanol electrooxidation. So while moving into the evolution of atomically precise noble metal nanoclusters, significant reduction in the nanoparticle size leads to a pronounced shift from plasmodic behavior to non-plasmodic behavior that you can see from the absorption spectra. And these such types of nanosystems are act as a link between the nanocrystal system and molecular chemistry, and this is due to the quantum confinement effect. Due to this quantum confinement effect, these types of nanosystems are produced molecular-like transitions, and these nanosystems are sub-nanometer sized systems are known as atomically precise noble metal nanoclusters, and these nanoclusters having a size of less than 2 nanometer with a metal core and a type of definite number of ligands. And normally we are synthesizing these atomically precise noble metal nanoclusters in lab. Previously it is a 2-phase synthesis. Now we are using a single-phase synthesis, that is a modified breast shipping method. So depends on this, due to this quantum confinement effect, we can tune the energy gap between the atomically precise noble metal nanoclusters using different methods like doping and heterometal doping, etc. So these nanosystems we can use as an application for the electrocatalysis due to this tunable quantum confinement effect in different applications like OER, water splitting reactions, carbon dioxide reduction reactions, and so on. But the problem lies in the field of these nanoclusters as an electrocatalyst is due to the presence of this ligand which is passivate around the metal core. So the exposition of the metal core is very less when it is coming to the electrocatalysis. So people are trying to do this electrocatalysis using, depends on the core size, doping and alloying in different methods. So while coming into the field of electrocatalysis, you know platinum hold a paramount position due to its exceptional energy with the hydrogen and low Tafel slope and exchange current density, etc. But the problem lies in the low abundance, high cost, activity loss and stability. So platinum needs a atomic level engineering in order to increase the reactivity towards the electrocatalysis. So we have designed a sub-nanometer platinum 6 nanoclusters, which we synthesized using a chemical reduction method, using triphenyl phosphine as the ligand, and the preparation and synthesis and formation of these nanoclusters are characterized and confirmed using the absorption spectra and the multi-dose spectroscopy, and the size we are analyzed using TEM and Hadaf-STEM analysis. So this synthesized nanocluster, again we confirmed with the bonding between the nanoclusters, we confirmed with the XPS analysis. And for the electrocatalytic application, we impregnated the platinum 6 nanoclusters into the Vulcan carbon, and which again we characterize using the XPS analysis, and morphology also analyzed with the TM analysis. So after this preliminary characterization, we have used these platinum 6 nanoclusters, which is incorporated into the carbon for the electrochemical applications. For that one, we are characterized using a basic electrocatalysis parameter, that is the hydrogen UPD. In the hydrogen UPD, you can see there is a negative shift in the hydrogen desorption peaks when compared to the commercial PTC. That means the hydrogen bonding with the platinum 6 is a very less stable, or the energy is very less when compared to the commercial PTC. While we are doing the CO stripping voltammetry, we could able to get a lower potential for the CO stripping. That is why we are using the adsorbed CO as a reducing agent for the decoration of Au3 plus on the surface of these platinum 6 nanoclusters as Au0. This is a schematic diagram for the decoration of Au atoms on the surface of these PT6 nanoclusters. And after this Au decoration, we have checked with the CO stripping voltammetry, but we couldn't able to find out any peak corresponding to the CO desorption, CO stripping. That means every COs are used for the decoration of these Au atoms. And from the CV analysis, you can see there is a formation of a gold oxidation and gold oxide reduction. That is the confirmation for the gold decoration. And the OCV and PBUPD also applied for this gold decoration on the surface of these PT6 nanoclusters. While we are checking the CO stripping voltammetry, you can see the CO peak is reduced. It is a broaden. That means some of the platinum atoms are only available for the CO. But and you can see there is a anomalous behavior, unique behavior we can see on the Au decorated one. Along with the CO stripping voltammetry, we could able to find out a hydrogen desorption peak also. That means platinums are available for CO stripping and also this hydrogen also. But unfortunately, we couldn't able to decorate any Au atoms on the surface of this commercial PTC. So after this Au decoration, we have used for this characterization uses XPS analysis, and the microscopy analysis also revealed the formation of Au atoms. And after this preliminary characterization, we have used these Au decorated nanoclusters for this electrocatalytic methanol oxidation, and we could able to find out a better electrochemical activity in terms of mass activity and specific activity. These are the impedance spectroscopy and blow dipole and summary of this methanol oxidation reaction. And while we are looking into the stability we could able to find out a better stability for the PT6 nanoclusters and Au decorated one when compared to the commercial PTC. And when CO tolerance, we are checking CO tolerance. These PT6 nanoclusters and Au decorated nanoclusters have a better CO tolerance when compared to the commercial PTC, because the commercial PTC only showing the CO stripping voltammetry in the presence of CO, but the other one showing the methanol oxidation in the presence of CO and methanol also. And the stability also revealed both the Au decorated one and PT6 NC show higher stability in terms of recycling and reactivation during the reactivation also. And the other one, the anodic potential of impact of this anodic potential, the PTC having a less stability when compared to the Au decorated one and PT6 nanoclusters. So in conclusion, we are preparing a PT6 nanoclusters, triphenyl phosphine stabilized PT6 nanoclusters, and we decorated AU atoms using the adsorbed CO for the decoration of these AU atoms, and which we are used for the enhanced methanol oxidation with better CO tolerance. And this work we published in the small. Thank you.
Presented and extremely fast presentation, but precisely on the right time.
Yes.
Thank you. I wanted to ask you that when platinum surface, carbon monoxide is sitting on it,
Yes, sir.
does it result in the one phosphine to come out? Or even with phosphine sitting there, carbon monoxide sits there? What is your understanding?
Sir, actually we tried to do this experimental setup completely in order to understand the mechanism, how the CO is attaching to the surface of PT6NCs and how it is AU, like what you ask, the one PPH3 molecule may be eliminated or not. We tried to do some DFT analysis that is still going on. I think it's while knowing the result only, I can come up with an exact conclusion. But I think the PPH3 molecule still it is there. That means that is why if the PPH3 molecule is going or leaving while the CO is coming, it may be exactly or some sort of behavior as it is showing like a commercial PTC. But when compared to the commercial PTC, even the PT6NCs itself showing as a higher activity and stability. Without AU also, sir.
Thank you. So PT6, is it octahedral to say that all the platinum atoms are of the same kind, or you have a square planar or such arrangement?
Sir, since we couldn't able to get any crystal structure, according to the PT6NCs, I couldn't able to answer the
Thank you.
exact structure, sir.
Very nice word. So you mentioned, I think, in terms of recyclability, that gold decorated platinum nanocluster is better than the other two, right?
Not recyclability, reactivation, ma'am.
Reactivation.
Actually, we have done that experiment running in the methanol involved sulfuric acid.
Okay.
And while we are recording a CV, then again we are taking the same electrode and run an reactivation in the methanol free electrolyte for some cycles, and again we are checking the methanol oxidation. Okay. So while it is going, this PTC is showing a sharp decrease from the starting onwards, but the other two, like our pristine nanocluster and also decorated one also showing the first increment, that is due to the presence of triphenyl phosphine and also in AU atoms also, then it is decreasing.
Okay, thank you.
Okay, thank you.
I'm Neslina, working under the guidance of Dr. Minimol M., Department of Chemistry, National Institute of Technology, Calicut. I'm glad to present my work, Interfacial Tension-Driven Synthesis of Morphologically Tuned P-Tellurium Nanocomposites at Diverse LL Interfaces. This is the graphical abstract of the work, and the work is published, and a patent has also been granted for the work. We devised an unconventional route and an emerging strategy of liquid-liquid interface for the synthesis of P-Tellurium nanocomposites at various LL interfaces. In a liquid-liquid interface synthesis, the interface acts as a quasi 2D template for the monomers and oxidants to diffuse and meet at the interface, and polymerization reaction is triggered. For the synthesis, I have chosen a well-known conducting polymer, poly-3,4-ethylene dioxythiophene, commonly known as P-DOT, due to its excellent film-forming properties, then good stability and tunable conductivity. This is the schematic representation for the synthesis. We have employed immiscible systems of 3 solvent systems of chloroform water, dichloromethane water, and hexane water. In this, tellurium 4+ ions are taken in the aqueous phase and E dot in the organic phase. After the reaction, we have seen product confinement at distinct phases. For chloroform water system, it is in the interface. For dichloromethane water system, it is in the bulk organic phase, and for hexane water, it is in the bulk aqueous phase. Interestingly, when we have taken the SEM analysis, we have found diverse morphology for the same composite. For chloroform water system, it is sheets. For DCM, it is sheets and spheres. And for hexane water system, it is solely spheres. The synthesis design was promptly inspired from the spontaneity of the Gibbs free energy of reaction for the redox couple involving conversion of tellurium 4 plus to Te0 and E dot to E dot radical cation. We have synthesized PTNC in two different ratios, 1:1 and 1:4, and from the EXARD analysis, crystalline peaks of hexagonal tellurium was observed, and for the Raman analysis, both peaks of P dot and tellurium were identified. And from both EXARD and Raman analysis, 1:4 ratio was found to be better. So we have chosen that for further in-depth analysis. Then this was chosen for microstructure morphology analysis. And as expected from the SEM analysis, we have seen for chloroform water system, it is P dot sheets with tellurium nanoparticles embedded in that. For dichloromethane water system, it was a mixed morphology with sheets as well as spheres. And for hexane water system, it is solely spheres, particularly causal structures with tellurium nanocores surrounded by P dot nanoshells. To get further insights, we have also analyzed from histogram profiles the average particle size, and for PTNC CW, it is 4.11, and for the other two systems, it is 146 nanometer. And also to analyze the distribution of TENPs in the polymer matrix, we have done EDS elemental mapping, and uniform distribution of TENPs in chloroform water system was seen, whereas an assorted distribution in the case of dichloromethane water system, and tellurium mostly concentrated in the inner regions for hexane water system. The topography analysis was also done from AFM tapping mode scan, and the sheet structure was identified for PTNC CW with an average sheet thickness of 141 nanometer. For DW system, it is particle size of 15 nanometer, and for HW system, colonized spheres of average diameter of 16 nanometer was observed. We have analyzed the interface confinement as well as bulk confinement using interfacial tension studies using pendant drop tensiometry in collaboration with the Department of Physics, NIT Calicut. And we have seen interfacial stabilization for chloroform water system up to 50 minutes. The drops were stable up to 50 minutes, and the corresponding fitting images after pendant drop technique is also shown along with the schematic illustration. The experiment that we have conducted on the lab scale for 24 hours for a comparison is in well agreement with the obtained results from pendant drop tensiometry. This is for DCM water system, where an initial stabilization indicating interface confinement, and then a gradual increase in interfacial tension indicating bulk movement was obtained for DCM system, and the corresponding optical images captured during reaction are also given. But in the case of hexane water system, since there is a meager difference in diffractive index between water and hexane, there imposed a practical difficulty in checking the IFT. However, we have observed from the pendant drop studies that only bulk aqueous confinement is there for hexane water system. Here, solvent polarity control diffusion dominates over interfacial tension-driven adsorption in the self-assembly process. We have also analyzed the electrocatalytic behavior, and PTNC in CW exhibited a capacitive behavior, whereas PTNC HW showed an oxidation peak for the electrochemical detection of ascorbic acid. Then linear range studies showed an LOD of 0.66 micromolar. With the scan rate analysis, it showed that mass transfer belongs to an adsorption control process. Anti-interference studies and repeatability studies were also done, with the mechanism of AA oxidation on PTNC is also given. So in conclusion, one-step in situ synthesis of tellurium-embedded P dot nanostructures using liquid-liquid interface-assisted polymerization has been done. 3 distinct liquid-liquid interface of chloroform water, dichloromethane water, and hexane water have been used. The choice of solvents and the interfacial tension played an integral role in determining the morphology of the structures. Diversity in the structures were confirmed from HRSM, HRTM and AFM analysis. Then temporal evolution of interfacial tension during the course of polymerization was analyzed using pendant drop tensiometry, and this was eventually compared for its electrochemical activity towards the enzyme-free detection of ascorbic acid. Thank you all for your kind attention.
Why not selenium?
Both tellurium and selenium can be chosen. Our team is now working on selenium as well. But we were impressed by that positive electrode potential of tellurium. That is, comes around 0.8 electron volt. So we can do polymerization without the aid of any external oxidants or reducing agents. Solely E dot and Te4 plus ions undergo redox reaction, and this is an in situ process where TNPs would get embedded in the P dot matrix. So minimal use of reagents can be done here.
So oftentimes people use tellurium because tellurium has certain semiconducting properties.
Yes, sir.
So inducing conductivity is something that people try. You have not looked at any conductivity aspect. Therefore, I asked this question, why tellurium?
One more reason is that tellurium is seldom explored as an electrode material. Actually, it is reported to have anti-cancer, antibacterial abilities, and some reports are also there where it is used for detecting hemoglobin in thalassemia persons and all. So, apart from treating tellurium as an electrode supercaps material, we have found the other way of utilizing it.
So the second point that I wanted to ask you was that all these particles in water often have surfactancy, and that has been used for your interfacial tension. Very nice. But often this very same technology or methodology can be used to understand rheology. You know, the viscosity of this particular, how much viscosity changes in a given medium. So that might add some value to you. Thank you.
Definitely, sir. We'll look into it.
Nice presentation. How did you find out the potential window for your three systems?
Potential window.
How did you find out that is the correct potential window?
For cyclic voltammetry,
Yeah.
we would be doing scans over a wide range, and then wherever we get that peaks, we would be shortening that range to enhance that nature of the peak. Also, we would refer from literature as well.
Literature. So,
Yes.
are you sure that there is no irreversibility involved in this potential range?
Mostly for ascorbic acid, it is not reported. It is that resolved oxidation peak mostly seen.
Hi, nice work, Sini. It is very interesting to see that based on the different solvent system, you are saying the important properties, right? So, how did you select those solvent pairs? Because there are so many solvent pairs can be made, right? So, what was the rationale behind selecting those cases?
Actually, we wanted confinement in 3 systems, at the interface, at the bulk organic phase, and at the bulk aqueous phase. So we have tried with some solvents, and we have sorted out from the one which is giving an interface confinement. Chloroform water mostly gives interface confinement. And for most of the system, hexane water, aqueous confinement. So likewise, we have chosen. And when we analyzed the morphology, it was quite interesting to see the role of solvent that is playing to give different physicochemical properties.
Right, right. Okay. And also like ascorbic acid sensing, right? So how is the selectivity?
Selectivity is good. We haven't seen much interference from the common interfering agents.
Now, did you have like lot of analytes, similar analytes and tested?
Yeah, we have tried with dopamine, then serotonin, then uric acid, all those things. But they were not seen interfering with ascorbic acid.
So what can be the reason for selectivity?
Reason, maybe that material is more favoring the oxidation of ascorbic acid rather than other analytes.
Thank you, Naslina.
With the obtained results from pendant drop tensiometry. This is for DCM water system, where an initial stabilization indicating interface confinement and then a gradual increase in interfacial tension indicating bulk movement was obtained for DCM system, and the corresponding optical images captured during reaction are also given. But in the case of hexane water system, since there is a meager difference in diffractive index between water and hexane, there imposed a practical difficulty in checking the IFT. However, we have observed from the pendant drop studies that only bulk aqueous confinement is there for hexane water system. Here, solvent polarity control diffusion dominates over interfacial tension driven adsorption in the self-assembly process. We have also analyzed the electrocatalytic behavior, and PTNC in CW exhibited a capacitive behavior, whereas PTNC HW showed an oxidation peak for the electrochemical detection of ascorbic acid. Then linear range studies showed an LOD of 0.66 micromolar. With the scan rate analysis, it showed that mass transfer belongs to an adsorption control process. Anti-interference studies and repeatability studies were also done with the mechanism of AA oxidation on PTNC is also given. So in conclusion, one-step in situ synthesis of tellurium embedded P dot nanostructures using liquid-liquid interface assisted polymerization has been done. 3 distinct liquid-liquid interface of chloroform water, dichloromethane water and hexane water have been used. The choice of solvents and the interfacial tension played an integral role in determining the morphology of the structures. Diversity in the structures were confirmed from HRTM and AFM analysis. Then temporal evolution of interfacial tension during the course of polymerization was analyzed using pendant drop tensiometry, and this was eventually compared for its electrochemical activity towards the enzyme-free detection of ascorbic acid. Thank you all for your kind attention.
Why not selenium?
Both tellurium and selenium can be chosen. Our team is now working on selenium as well. But we were impressed by that positive electrode potential of tellurium. That is, comes around 0.8 electron volt. So we can do polymerization without the aid of any external oxidants or reducing agents. Solely E dot and Te4 plus ions undergo redox reaction, and this is an in situ process where TNPs would get embedded in the P dot matrix. So minimal use of reagents can be done here.
So oftentimes people use tellurium because tellurium has certain semiconducting properties.
Yes, sir.
So inducing conductivity is something that people try. You have not looked at any conductivity aspect. Therefore, I asked this question, why tellurium?
One more reason is that tellurium is seldom explored as an electrode material. Actually, it is reported to have anti-cancer, antibacterial abilities, and some reports are also there where it is used for detecting hemoglobin in thalassemia persons and all. So, apart from treating tellurium as an electrode supercaps material, we have found the other way of utilizing it.
So the second point that I wanted to ask you was that all these particles in water often have surfactancy, and that has been used for your interfacial tension. Very nice. But often this very same technology or methodology can be used to understand rheology. You know, the viscosity of this particular, how much viscosity changes in a given medium. So that might add some value to you. Thank you.
Definitely, sir. We'll look into it.
Nice presentation. How did you find out the potential window for your 3 systems?
Potential window.
How did you find out that is the correct potential window?
For cyclic voltammetry,
Yeah.
we would be doing scans over a wide range, and then wherever we get that peaks, we would be shortening that range to enhance that nature of the peak. Also, we would refer from literature as well.
Literature. So, are you sure that there is no irreversibility involved in this potential range?
Mostly for ascorbic acid, it is not reported. It is that resolved oxidation peak mostly seen.
Hi, nice work, Sini. It is very interesting to see that based on the different solvent system, you are saying the important properties, right? So how did you select those solvent pairs? Because there are so many solvent pairs can be made, right? So what was the rationale behind selecting those cases?
Actually, we wanted confinement in 3 systems, at the interface, at the bulk organic phase, and at the bulk aqueous phase. So we have tried with some solvents, and we have sorted out from the one which is giving an interface confinement. Chloroform water mostly gives interface confinement. And for most of the system, hexane water, aqueous confinement. So likewise, we have chosen. And when we analyzed the morphology, it was quite interesting to see the role of solvent that is playing to give different physicochemical properties.
Right, right. Okay. And also like ascorbic acid sensing, right? So how is the selectivity?
Selectivity is good. We haven't seen much interference from the common interfering agents.
Now, did you have like lot of analytes, similar analytes and tested?
Yeah, we have tried with dopamine, then serotonin, then uric acid, all those things. But they were not seen interfering with ascorbic acid.
So what can be the reason for selectivity?
Reason, maybe that material is more favoring the oxidation of ascorbic acid rather than other analytes.
Okay. Thank you.
Thank you, Naslina.
I am Sini KS, research scholar from the Department of Chemistry, St. Joseph's College, Autonomous Devagiri, Calicut. I am working under the supervision of Dr. Shinu VS. My topic is copper-catalyzed N-alkylidene bisamide synthesis, a versatile reaction to access promising lead compounds. Look at this image. What we can see that an elephant is loading the logs. In the second image, a machine is doing the same. By comparing these two, we can say that we can see that the efficiency, productivity, safety, time management, everything is superior in the second image. But the making of that machine is definitely inspired from the natural source. So keep this idea in your mind. Let's move on to biological system. Let me introduce a set of compounds called peptidomimetics. As the name indicates, peptidomimetics derived from peptides or proteins, they can mimic the activity of proteins where they fail to do their activity. So peptidomimetics outperform the function. There should be no strict structural similarity for doing this particular action. So mainly my work is focused on peptidomimetics. I am interested in doing inhibitors for PTP1B enzyme. PTPs are signaling agents, but their disintegration leads to the cancer, type 2 obesity, or even neurological diseases, etc. So these are some of the triazole-based inhibitors available. We also designed and developed a set of compounds called bispeptidotriazole. This part of work is published in the Journal of Organic Chemistry. In that work, we also proposed an efficient protocol for accessing symmetrical bisamides. Why symmetrical bisamides? Symmetrical bisamides are well prominent in biological or pharmaceutical domain, but there is no active, well-established protocol for accessing it. The conventional method is to access is an acid-catalyzed reaction with the aldehyde and amide. So the substrate scope is limited to bis acetamides or bis benzamides. So here we are presenting a very well-established, very promising reaction using nitriles. Actually, this particular reaction emerged from our curiosity to know what would be the product if we are removing this enolizable ketone from this particular multi-component reaction. This was then named as beta-acetamidocarbonyl synthesis. Now it is termed as Iqbal-3CR. Through our first publication, it happened. Now it is known as named reaction in the name of Dr. Javed Iqbal. So Iqbal-3CR title, first publication is also out in Chemistry Select, and our another piece of work. On coming to the bisamide synthesis, we have developed a 27 compound library, including various aldehydes, aliphatic aromatic aldehydes, aliphatic aromatic substituted and unsubstituted nitriles. So among that, one molecule was found really fascinating to us. That is nothing but this particular compound. Here we can see the acid functionality and amide functionality together. In a biological aspect, These two functionalities are very important. So on expanding, we are planning to expand the compound library of this particular molecule. We did our reaction with a developed protocol. We got the product with 6 hours of reaction in room temperature. We expanded the compound library using these 3 molecules, and by that we are targeting to increase the substrate scope, targeting derivatization via carboxylic acid functionality definitely, and focusing compounds with improved activity and coupled with Ugi reaction to create tetrapeptides in future as a part of our continuation of the work to create beta tripeptidyl ketones. For further support, I have also included the characterization data available. And in conclusion, we have expanded the NN-alkylidine bisamide compound library successfully with the 3 more novel compounds. And it was obtained in good yield and purity without the need of column purification. And focus on improving the activity of lead compounds through functionalization. And explore the application of this particular synthesis with click reaction and other coupling reaction like Ugi reaction. And biologically auspicious compound can be developed through derivation of this particular scaffold too. And finally, we accessed a biologically relevant NN-alkylidine bisamide as promising lead compounds. These are the references, and thank you all.
So, one thing, what was the role of copper sulfate in that reaction?
Copper sulfate actually activates the aldehyde to perform the reaction. We performed with varieties of Lewis acid catalyst. It was found copper sulfate worked well. So we just proposed a mechanism. In that, we can say that aldehyde activated by this copper sulfate by a complex formation.
Okay, okay. And also, like in your library, there are different yields I saw.
Sorry?
In the library synthesis, yields are it's a wide range of the yield, right? Yield of the reaction.
Yeah.
So based on the functional group, I think. So did you see any relation?
Yeah, definitely. In most of the cases, while using nitrile benzonitrile, we get good yield. And dealing with the aldehyde, in the case of aldehyde, para-substituted aldehydes yielded more than unsubstituted aldehyde or even electron donating aldehydes. So electron withdrawing aldehydes giving more result. And in the case of nitriles, benzonitrile is first, then chlorobutronitrile, then acetonitrile, last butronitrile.
Okay, thank you.
Thank you, sir. Thank you, ma'am.
I would like to thank Dr. Mindu Porel and Professor Deepak Chopra for evaluating the presentations. I also thank all the presenters, Lakshmi V. Menon, Aman Kumar Jha, Amrita TP, Maimuna Paloli, Neslina P, and Sini KS for presenting their wonderful works at EFCS. Thank you all. Moving to the next session. Thank you.